3 days from now, on December 19th, 2025, something from another star system will make its closest approach to Earth. And in the last 72 hours, it changed colour. Again, for the third time. First it was red, then it glowed an eerie green. And now, as multiple astronomers across the planet have independently confirmed, 3I-ATLAS is turning gold. The last time we witnessed this exact transformation in a comet, that object shattered into pieces within days. The question racing through the scientific community right now is simple. Is 3I-ATLAS about to break apart before our eyes? Or is something else happening entirely? Something our models cannot explain? Tonight, we're going to examine every piece of evidence, every anomaly, every theory, from the mundane to the extraordinary. By the time we reach the end, you will understand why 80 observers from the United Nations International Asteroid Warning Network are watching this object around the clock, why the anti-tail of 3I-ATLAS now stretches farther than the distance from Earth to the Moon, and why some scientists believe this interstellar visitor is not behaving like any comet we have ever seen. Stay with me until the very end, because what happens in the next 72 hours could rewrite everything we thought we knew about visitors from beyond our solar system. Before we begin, always remember to like this video, and if you enjoy these calming deep dives into the mysteries of our universe, do not forget to subscribe and hit that notification bell so you never miss an update. Let us begin with what happened over the past 72 hours, because the timing here is extraordinary. On December 10th, 2025, an amateur astronomer named Alberto Quano Vodniza captured an image of 3I-ATLAS that immediately sparked conversation across the astronomical community. The object, which had been glowing a distinctive green since emerging from behind the sun in November, was displaying something unexpected, a golden hue. At first, many dismissed this as an artifact of the imaging equipment, perhaps a filter issue or atmospheric distortion. But then more observations began pouring in. December the 13th brought confirmation from Tony Scarmato in Calabria, Italy, using a 0.25-metre telescope. December 14th saw Dan Bartlett capture the object from June Lake, California, with a 14-inch instrument and a total integration time of 2 hours and 22 minutes. The verdict was consistent across continents and across equipment. 3I-ATLAS is shifting from green to gold. Think about that for a moment. An object that originated around another star, perhaps 7 to 14 billion years ago, according to recent estimates. An object that has travelled through the cold darkness of interstellar space for eons, is now changing its appearance in real time as we watch. And this is not the first transformation we have witnessed. When 3I-ATLAS was first detected on July 1st of this year by the Atlas Survey Telescope in Chile, it presented with a deep red coloration. This red was attributed to organic compounds on its surface, complex carbon-based molecules that had accumulated during its long journey through the galaxy. The redness was so pronounced that astronomers immediately noted it was darker and more intensely coloured than our previous interstellar visitors, Oumuamua and Borisov. The organics suggested that 3I-ATLAS had spent considerable time collecting material from interstellar space, possibly from the remnants of exploded stars, from nebulae, from the diffuse matter that permeates the void between stellar systems. Then came September. As 3I-ATLAS crossed the critical threshold of 2.5 astronomical units from the Sun, what astronomers call the waterline, everything changed. Water ice began sublimating aggressively. The coma, that envelope of gas and dust surrounding the nucleus, erupted with activity, and the colour shifted from red to green. This green glow is well understood in cometary science. It comes from diatomic carbon, molecules consisting of 2 carbon atoms bonded together. When solar ultraviolet radiation strikes these molecules, they become excited and emit light at wavelengths our eyes perceive as green. We have seen this in countless solar system comets. The famous Devil comet 12P Pons Brooks displayed this exact green coloration during its 2024 flyby. It is, in many ways, the signature colour of an active comet. But gold is different. Gold is rare. Gold is unsettling. To understand why this matters, we need to look at what happened to another object just weeks ago, Comet C2025 K1-ATLAS, discovered by the same survey telescope that found 3I-ATLAS, made an extremely close approach to the Sun on October 8th. It flew within 50 million kilometres of our star, 4 times closer than 3I-ATLAS managed during its own perihelion. Many astronomers expected K1 to be destroyed by this encounter. The gravitational stress, the intense heating, the rapid sublimation of volatile ices, all of these forces should have torn the object apart. Instead, K1 survived, and when it emerged from the sun's glare, it was glowing gold. Astrophotographer Dan Bartlett, the same observer who recently captured 3I-ATLAS in its golden phase, photographed K1 on October 29th and noted something remarkable. The comet was displaying a red-brown golden colour rarely seen in comets. Astronomer David Schleicher at Lowell Observatory examined the spectroscopic data and found that K1 had a surprising lack of carbon-bearing molecules, specifically dicarbon, carbon monoxide and cyanide. Only 2 other comets in recorded history have shown such severe carbon depletion, and then K1 began to fragment. By November 11th, telescopic observations confirmed that the comet had split into at least 3 distinct pieces. The golden colour, it seemed, had been a warning sign, a signal that the internal chemistry and structure of the object were fundamentally changing, that the volatile ices binding the nucleus together were exhausted, that the end was near. Now 3I-ATLAS is following the same pattern, red to green to gold, and it is doing so while moving into the exact same region of sky, the constellation Leo, where K1 underwent its transformation. The coincidence is striking enough that some observers have begun to wonder if there is something more than coincidence at work here. Both objects bear the Atlas designation. Both underwent dramatic colour shifts. Both are transitioning to gold as they enter Leo, the constellation of the Lion, historically associated with royalty and power. The symbolism has not been lost on those who track such things, though we must be careful to separate poetic observation from scientific analysis. What does the gold colour actually indicate from a chemical standpoint? The leading hypothesis is that 3I-ATLAS has essentially burned through its reservoir of carbon-bearing compounds. During its approach to the Sun and passage through perihelion on October 29th, the intense solar radiation drove off the volatile gases that had been producing the green glow. The dicarbon molecules, the cyanogen, the carbon monoxide, all of these were stripped away or photodissociated, broken apart by ultraviolet light. What remains is a dust-dominated coma, material that reflects sunlight in the warmer wavelengths rather than emitting the characteristic green of excited carbon molecules. In essence, 3I-ATLAS may be exhausted. The exotic materials it collected during its billions of years wandering through interstellar space, the organics that gave it its initial red colour, the volatile ices that powered its green phase, all of these could be depleted. What we are seeing now might be the bare bones of an ancient traveller, stripped of its accumulated treasures by its close encounter with our star. But here is where the story becomes complicated. Here is where our intuition breaks down. If 3I-ATLAS has lost most of its volatile material, if it is truly entering an exhausted phase, then its activity should be decreasing. Its coma should be fading. Its brightness should be dropping rapidly as it moves away from the Sun. And while the object has indeed dimmed somewhat since its post-perihelion peak, it remains stubbornly active. Images from December 14th and 15th show not just the golden coma, but a prominent feature that has been present since the very first Hubble Space Telescope observations back in July, an anti-tail pointing directly toward the Sun. This anti-tail is not a minor feature. According to the latest measurements, it now extends approximately 500,000 kilometres from the nucleus of 3I-ATLAS. That is larger than the distance from Earth to the Moon. Material is streaming from this object in a direction that, under normal circumstances, should be impossible. Solar radiation pressure pushes cometary material away from the Sun. That is why comet tails always point away from our star. Yet 3I-ATLAS has maintained a persistent, coherent structure pointing directly into the solar wind, directly toward the source of the radiation that should be pushing it backward. Harvard astrophysicist Avi Loeb has been tracking this anomaly since July. In his latest analysis from December 15th, he notes that to reach a scale of 500,000 kilometers over the 45 days since perihelion, the sunward speed of the material in the antitail must be at least 130 meters per second relative to the nucleus. Whether this speed can be maintained by sublimated dust or gas from pockets of ice facing the solar wind remains to be studied, he writes. The alternative is a jet from a technological thruster. Now, we must be very careful here. Loeb has been a controversial figure in the astronomical community, and his suggestions about technological origins for interstellar objects have drawn sharp criticism from many of his peers. The majority of scientists studying 3I-ATLAS maintain that it is a natural comet, albeit an unusual one. The anti-tail, they argue, can be explained by large particles that are less affected by solar radiation pressure. Particles massive enough to resist being pushed backward and instead follow trajectories influenced primarily by the object's own motion and gravitational interactions. But even the skeptics acknowledge that 3I-ATLAS is not behaving quite like any comet we have seen before. The persistence of the anti-tail across multiple observation epochs, from pre-perihelion in July to post-perihelion in November and December, is genuinely puzzling. For solar system comets, anti-tails are typically a perspective effect, appearing briefly when Earth crosses the comet's orbital plane. 3I-ATLAS's sunward extension shows no such geometric dependency. It appears to be a physical, structural feature of the object itself, and that brings us back to the golden transformation. If 3I-ATLAS is indeed running out of volatile material, if its green phase represented the last gasp of active sublimation, then what is producing this massive anti-tail? Where is the energy coming from? What mechanism is driving material sunward at speeds exceeding 100 meters per second? The answers may come sooner than we expect. In just 3 days, on December 19th, 3I-ATLAS will make its closest approach to Earth at a distance of approximately 270 million kilometers. That same day happens to coincide with a new moon, meaning that observers will have the darkest possible skies for their observations, no lunar glare to compete with, no scattered moonlight to wash out faint details. It is, as Loeb himself has noted, an ideal observing night for Earth-based telescopes. The James Webb Space Telescope is scheduled to make new observations in December. The Hubble Space Telescope has already provided multiple images, including a post-perihelion view from November 30th that clearly shows the teardrop-shaped coma and sunward extension. Ground-based observatories from Chile to Hawaii to Thailand to Italy are training their instruments on this object every clear night. What they find in the coming days could settle the question of whether 3I-ATLAS is fragmenting, whether its golden colour is the herald of its destruction, as it was for K1-ATLAS. Or they might discover something else entirely, something that challenges our assumptions about what an interstellar object can be. Because there is another possibility we have not yet considered. What if the gold is not a sign of death, but of revelation? What if the stripping away of volatile gases is exposing something that was hidden beneath, something that accumulated over billions of years of travel through the cosmos? We know that 3I-ATLAS carries an unusual composition. Spectroscopic analysis has revealed nickel emissions without corresponding iron, a ratio that defies the typical chemistry of solar system comets. We know that its surface shows evidence of radiation damage extending up to 20 meters deep, suggesting exposure to cosmic rays over timescales that dwarf the age of our own solar system. We know that its trajectory is aligned within 5 degrees of the ecliptic plane of our solar system, a coincidence with a probability of just 0.2%, and we know that in 72 hours we will have our best opportunity to study this object before it begins its long journey toward Jupiter and beyond, never to return. The gold metamorphosis of 3I-ATLAS may be its final transformation, or it may be just the beginning of the true mystery. Because as we will explore in the next chapter, the anti-tail is not the only feature of this object that refuses to obey the rules we thought we understood. The sunward jet that defies physics. There is a rule in cometary science that has held true for as long as we have been observing these icy wanderers. Material ejected from a comet flows away from the sun, always. The mechanism is elegant in its simplicity. Solar radiation exerts pressure on the particles streaming from a comet's nucleus, pushing them backward, sculpting the iconic tails that have inspired wonder and fear throughout human history. The ion tail, composed of charged particles, points directly away from the sun, driven by the solar wind. The dust tail curves gently, its trajectory a compromise between the comet's forward motion and the relentless push of sunlight. But both tails, in every comet we have ever studied, share one fundamental characteristic. They point away from our star. 3I-ATLAS did not receive this memo. Since the very first high-resolution image captured by the Hubble Space Telescope on July 21st of this year, 3I-ATLAS has displayed a feature that should not exist. A coherent stream of material extending toward the sun, not away from it. Toward it. The initial Hubble image showed a teardrop-shaped coma with its elongation pointing in the sunward direction, precisely opposite to what our models predict. At the time, some astronomers suggested this might be a temporary perspective effect, a geometric artifact that would resolve itself as Earth's position relative to the comet changed. This explanation has worked for solar system comets in the past. When Earth crosses a comet's orbital plane, the viewing angle can create the illusion of a sunward extension, even when the material is actually flowing in the expected direction. But 3I-ATLAS refused to cooperate with this explanation. The sunward feature persisted through August. It persisted through September. It was still present when the object emerged from solar conjunction in November. And as of December 15th, the anti-tail has not only persisted, but grown to extraordinary proportions. 500,000 kilometers, 500,000 kilometers of material streaming toward the sun. To put this in perspective, the average distance from Earth to the Moon is approximately 384,000 kilometers. The anti-tail of 3I-ATLAS is now larger than that distance. You could fit the entire Earth-Moon system inside this structure with room to spare. The latest images from amateur astronomers around the world confirm what the professional observatories have been documenting. Tirasak Thalawang captured the object on December the 13th from Thailand, using a modest 0.26-meter telescope. The rotational gradient brightness map, processed using a Larsen-Sekanina filter to enhance subtle features, shows the anti-tail pointing unmistakably toward the lower left of the frame, directly toward the sun. Dan Bartlett's December 14th image from California, taken with a larger 14-inch instrument, reveals not just the anti-tail, but a distinct green-blue coloration in the sunward extension, suggesting active emission processes are occurring within this impossible structure. How do we explain material moving toward the sun when every force we understand should be pushing it away? 3 scientific papers have attempted to address this question, and their explanations reveal just how far outside normal parameters 3I-ATLAS has pushed our understanding. The first 2 papers, co-authored by Avi Loeb and Eric Quito, propose that the anti-tail is composed of ice fragments shed from the sun facing side of the nucleus. These fragments, the authors argue, are small enough to sublimate rapidly but large enough to resist being pushed backward by radiation pressure during their brief existence. They evaporate before the solar wind can significantly alter their trajectories, creating the appearance of a sunward stream. It is a clever explanation that works within known physics, though it requires some fine-tuning of particle sizes and sublimation rates. The third paper, published by Loeb alone on December 8th, offers a more provocative hypothesis. What if the anti-tail is not composed of ice fragments at all? What if it represents a swarm of solid objects that lag behind 3I-ATLAS because the main body is experiencing non-gravitational acceleration away from the Sun? This scenario would mean that 3I-ATLAS itself is being pushed outward by some mechanism beyond solar gravity and radiation pressure, while the objects in its wake, not experiencing this additional acceleration, appear to fall behind and thus point sunward relative to the main nucleus. The evidence for non-gravitational acceleration comes from tracking data provided by the Jet Propulsion Laboratory's Horizon system. Since November, the orbital solutions for 3I-ATLAS have required the inclusion of a small but measurable acceleration component that scales inversely with the square of the distance from the Sun, exactly matching the behaviour of solar gravity itself. The magnitude is tiny, approximately 0.02% of the gravitational acceleration, but it is persistent and it is real. Something is pushing 3I-ATLAS in a way that cannot be explained by gravity alone. For most comets, non-gravitational acceleration is attributed to outgassing. When volatile ices sublimate, the escaping gas acts like a tiny rocket thruster, nudging the nucleus in the opposite direction. This effect has been measured in numerous solar system comets, and was even invoked to explain the anomalous acceleration of our first interstellar visitor, Oumuamua. But here is where 3I-ATLAS presents a puzzle. The amount of outgassing required to produce the observed acceleration is enormous. Calculations suggest that 3I-ATLAS would need to be losing mass at a rate of approximately 2 million kilograms per second at perihelion. That is 2,000 metric tons of material every single second streaming away into space. If this mass loss were occurring, we should see evidence of it. We should see an expanding cloud of gas surrounding the object detectable through spectroscopy. We should see dramatic brightening events as fresh material is exposed. We should see, frankly, a much more impressive tail than what we actually observe. Instead, 3I-ATLAS displays a relatively compact coma with the bizarre sunward extension that continues to defy easy explanation. The Hubble Space Telescope image from November 30th, taken approximately 1 month after perihelion, provides our highest resolution view of the anti-tail to date. The image was captured using the f350 LP filter aboard the Widefield Camera 3, and it shows something that has caught the attention of observers worldwide. The coma is not chaotic. It is not the messy asymmetric structure we typically see in actively outgassing comets. Instead, it displays an almost perfectly spherical glow extending approximately 40,000 kilometres in all directions from the central condensation. And from this spherical envelope emerges the narrow, elongated anti-tail, sharper and more defined than in any previous observation. The word that keeps appearing in scientific discussions of this feature is coherent. The anti-tail is coherent. It maintains its structure across hundreds of thousands of kilometres. It does not diffuse or scatter in the way that a cloud of gas or small dust particles should. It behaves, in some ways, more like a directed stream than a random ejection of material. What could produce such a coherent structure? One possibility, favoured by those seeking conventional explanations, involves the geometry of the nucleus itself. If 3I-ATLAS has a highly elongated shape and rotates with one end consistently pointed toward the Sun, jets of material could emerge preferentially in the sunward direction. The rotation would provide the momentum, and the jet geometry would explain the coherence. But this explanation requires that the jets maintain their orientation despite the measured rotation period of approximately 16 hours. Over the timescales involved, approximately 45 days since perihelion, the nucleus would have completed dozens of rotations. Any jets should be smeared out, their material distributed in a spiral pattern rather than a coherent linear stream. Yet the latest images show tightly collimated jets extending to distances larger than 1,000,000 kilometers, maintaining their orientation across multiple observations. This persistence is, in Loeb's terminology, the 12th anomaly of 3I-ATLAS, one entry on a growing list of features that distinguished this object from any comet we have studied before. Let us take a moment to appreciate what we are actually observing here. An object from another star system, travelling at approximately 61 kilometers per second, is displaying a feature that points toward the Sun rather than away from it. This feature has persisted for nearly 6 months across multiple observation epochs. It now extends farther than the distance from Earth to the Moon. The object simultaneously shows evidence of non-gravitational acceleration that cannot be fully explained by the visible outgassing. And all of this is happening as the object changes colour in ways that mirror a solar system comet that subsequently fragmented. The conservative interpretation is that 3I-ATLAS represents a new class of comet, one formed in conditions so different from our own solar system that our models simply do not apply. Perhaps the ice composition is unusual, with exotic volatiles that sublimate differently than the water and carbon dioxide we expect. Perhaps the dust-to-gas ratio is extreme, with large particles dominating the coma in ways that alter the radiation pressure dynamics. Perhaps the internal structure is fundamentally different, a rubble pile held together by processes we do not yet understand. The less conservative interpretation, and one that has captured the imagination of millions following this story online, is that 3I-ATLAS is not entirely natural, that some component of its behaviour reflects design rather than random cosmic processes, that the anti-tail might be, as Loeb has suggested in his most provocative moments, the exhaust from a technological propulsion system. We must be absolutely clear about the epistemic status of this latter hypothesis. There is no direct evidence that 3I-ATLAS is artificial. No radio signals have been detected that indicate intelligent communication. No manufactured structures have been resolved in any imagery. The object displays cometary activity, complete with gas emission, dust production, and a measurable coma. The vast majority of astronomers studying 3I-ATLAS conclude that it is a natural comet, extraordinary in its properties, but not supernatural or artificial in its origin. But science proceeds by taking anomalies seriously, by not dismissing observations simply because they are inconvenient or uncomfortable. And the anti-tail of 3I-ATLAS is genuinely anomalous. It demands explanation. Whether that explanation ultimately involves exotic ice chemistry, unusual nucleus geometry, or something we have not yet conceived, the process of seeking answers will advance our understanding of interstellar objects regardless of the outcome. What makes the current moment so significant is that we're about to get much better data. The December 19th closest approach will bring 3I-ATLAS to within 270 million kilometers of Earth, the minimum distance of its entire passage through our solar system. At this range, ground-based telescopes with 30-centimeter apertures or larger should be able to detect the object visually. Professional observatories will capture spectroscopic data with unprecedented detail. The James Webb Space Telescope, scheduled for observations this month, will examine the infrared signatures of the coma, potentially identifying molecules that are invisible to optical instruments. If the anti-tail is composed of ice fragments, Webb should detect the spectral signatures of water and other volatiles in the sunward stream. If it is composed of solid particles, the infrared emission should reveal their thermal properties and potentially their composition. If the non-gravitational acceleration is driven by outgassing, the spectroscopy should show clear evidence of gas production rates consistent with the required mass loss. And if none of these expectations are met, if the data continues to confound our models, if the anti-tail remains inexplicable, if 3I-ATLAS refuses to behave like any comet we know, then we will have learned something profound about the diversity of objects that wander between the stars. We will have discovered that the universe is stranger than we assumed, that our sample size of 2 previous interstellar visitors was far too small to prepare us for what 3I-ATLAS represents. Whether that strangeness reflects exotic natural processes or something more deliberate, we will not know until we look. The anti-tale of 3I-ATLAS is not just a scientific puzzle, it is an invitation to question assumptions, to gather data, to let the evidence guide us wherever it leads. In 3 days, when the object makes its closest approach, we will have our best opportunity to accept that invitation. But the anti-tale is not the only feature of 3I-ATLAS that demands our attention. As we mentioned briefly, this object shares its designation with another comet that recently underwent a dramatic transformation. And the parallels between 3I-ATLAS and K1-ATLAS extend far beyond their names. In fact, their paths through our solar system have intersected in ways that some observers find deeply unsettling. Because both objects are currently transiting through the same constellation, both have shifted to golden coloration, and one of them has already shattered into pieces. When two comets enter, Leo, there is something almost theatrical about the way our universe stages its events. Two objects bearing the same name, discovered by the same telescope network, undergoing the same chromatic transformation, passing through the same region of sky within weeks of each other. If a screenwriter had pitched this scenario for a science fiction film, the producers might have rejected it as too coincidental, too on the nose. Yet here we are, watching it unfold in real time. Comet C 2025 K1-ATLAS was discovered in May of this year by the Asteroid-Terrestrial Impact Last Alert System, the same network that would detect 3I-ATLAS less than 2 months later. K1 was a solar system comet, born in the Oort cloud at the frozen edges of our celestial neighbourhood, making its first journey into the inner solar system. It was, by all accounts, pristine material, never before heated by the sun, carrying the chemical fingerprints of the era when our solar system was young. K1's trajectory brought it dangerously close to our star. On October 8th, it passed within 50 million kilometres of the sun, 4 times closer than 3I-ATLAS would manage during its own perihelion 3 weeks later. At such proximity, the gravitational stresses are immense, the heating is extreme. Many astronomers predicted that K1 would not survive the encounter. It was too small, too fragile, too volatile. The sun would tear it apart. But K1 emerged from perihelion intact. Battered, certainly. Changed, absolutely, but intact. And when astrophotographer Dan Bartlett captured it on October 29th from Dune Lake, California, the image revealed something unexpected. K1 was glowing gold. Not the green of diatomic carbon that characterizes active comets. Not the white of reflected sunlight that we see in dormant bodies. Gold. A warm, amber hue that spoke of fundamental chemical changes within the object. Bartlett's observation was not isolated. Multiple photographers across California and Arizona confirmed the same coloration. Astronomer David Schleicher at Lowell Observatory conducted spectroscopic analysis and found that K1 had lost most of its carbon-bearing molecules. The dicarbon, the carbon monoxide, the cyanide, all the compounds that typically produce the green glow in cometary comas, were severely depleted. Only 2 other comets in recorded history had shown such extreme carbon depletion. At the time, the astronomical community was focused primarily on 3I-ATLAS, which was approaching its own perihelion and would soon disappear behind the sun from Earth's perspective. K1 was the other Atlas comet, interesting but overshadowed by its interstellar cousin. Few people noticed that K1 had begun drifting into the constellation Leo, the celestial lion that has represented royalty and power across countless human cultures. Then K1 began to fragment. On November 10th, observers detected the first signs of structural failure. By November 11th, it was confirmed. The comet had split into at least 3 distinct pieces. Gianluca Massi of the Virtual Telescope Project captured images showing multiple subnuclei and clouds of debris where there had once been a single coherent body. The fragmentation continued over the following days, with each piece fluctuating in brightness and position as the remnants of K1 scattered into space. The golden colour, it turned out, had been a warning sign, a signal that the internal chemistry supporting the comet's structure had been exhausted. When the volatile ices that bind a cometary nucleus together are depleted, the body loses its cohesion. Solar heating creates thermal stresses that the weakened structure cannot withstand. The nucleus cracks, then fractures, then disintegrates entirely, and now 3I-ATLAS is following the same trajectory. Not the physical trajectory through space, though there are interesting parallels there as well, but the chromatic trajectory. Red to green to gold. The same sequence that K1 displayed before its destruction. As of mid-December, 3I-ATLAS has entered the constellation Leo. It is currently positioned between Virgo and Leo, drifting steadily toward the heart of the celestial lion. On December 19th, when it makes its closest approach to Earth, it will be located just under Regulus, the brightest star in Leo. By December 27th, it will pass within 1.8 degrees of Regulus, deep within the constellation that witnessed K1's transformation and demise. The symbolism has not been lost on observers. Leo is associated with the sun in astrological traditions with gold and amber colours, with lions and royalty. 2 Atlas comets, both turning gold, both entering Leo, one already shattered. There is a poetic resonance here that transcends the purely scientific, though we must be careful not to let symbolism substitute for analysis. What are the actual physical parallels between these two objects, and what do they tell us about what might happen to 3I-ATLAS in the coming days? The first parallel is the colour shift itself. Both objects transitioned from green to gold after perihelion, suggesting similar chemical processes at work. The depletion of carbon-bearing molecules appears to be the primary driver. When diatomic carbon is no longer being produced in sufficient quantities to dominate the coma's optical signature, the reflected sunlight from dust particles becomes the primary source of colour. Gold or amber hues indicate dust that absorbs blue light preferentially, likely due to the presence of iron-bearing silicates or complex organic residues. The second parallel is the timing relative to perihelion. K1's colour shift occurred within days of its closest approach to the Sun. 3I-ATLAS has taken longer, approximately 6 weeks post-perihelion, but this is consistent with its greater distance from the Sun during perihelion. K1 came within 50 million kilometres of the solar surface. 3I-ATLAS only reached 210 million kilometres, roughly 4 times farther. The heating was correspondingly less intense, and the chemical changes have proceeded more slowly. The third parallel, and this is where things become troubling, is the activity level. K1 displayed elevated activity in the weeks before fragmentation, with outbursts observed between October 31st and November 4th. 3I-ATLAS has been showing its own elevated activity, including the persistent anti-tail and the multiple jets documented in recent imagery. If outbursts precede fragmentation, then 3I-ATLAS may be approaching a similar critical point, but there are also critical differences that give reason for cautious optimism. 3I-ATLAS is almost certainly larger than K1 was. Hubble Space Telescope observations constrain the nucleus diameter to somewhere between 440 metres and 5.6 kilometres. Even at the lower end, this is substantially larger than the typical Oort cloud comet that fragments near the Sun. Larger nuclei have more thermal inertia, meaning they heat and cool more slowly, reducing the thermal stresses that drive fragmentation. Furthermore, 3I-ATLAS has a different origin and presumably different composition. K1 was a solar system object, formed from the same primordial material as our planets. 3I-ATLAS comes from another star system entirely, possibly one that formed billions of years before our own Sun ignited. The ice chemistry, the dust composition, the internal structure, all of these could be fundamentally different in ways that affect survivability. There is also the question of thermal history. K1 was making its first approach to the Sun, experiencing intense heating for the first time in its existence. 3I-ATLAS, according to the leading hypothesis about its origin, was once a short-period comet around its host star. It underwent hundreds or even thousands of close approaches before being ejected into interstellar space. This prior thermal processing may have removed the most volatile and structurally weak components, leaving behind a nucleus that is more resilient to solar heating. The evidence from 3I-ATLAS's perihelion passage supports this interpretation. Despite passing within 1.4 astronomical units of the Sun and experiencing heating of approximately 735 watts per square metre, the nucleus appears to have maintained its integrity. The post-perihelion images from Hubble show a single coherent object, not the multiple fragments that would indicate breakup. The anti-tail, whatever its origin, emerges from a central source rather than distributed debris. But the gold colour is still concerning. The shift away from carbon-bearing emissions suggests that the volatile reservoirs are indeed becoming depleted. And if 3I-ATLAS is running out of the ices that have been driving its activity, then the internal pressures that maintain structural cohesion may be changing in unpredictable ways. The next several days will be critical. The closest approach on December 19th will provide our best observations yet, but it is also the period of maximum gravitational stress. While 3I-ATLAS will be 270 million kilometres from Earth, it will be experiencing the cumulative effects of its solar encounter. The heating from perihelion takes time to penetrate into the interior of a nucleus. Thermal waves propagate slowly through porous, icy material. The maximum internal temperature may not be reached until weeks or even months after the closest approach to the Sun. This means that even if 3I-ATLAS survived perihelion apparently intact, the structural crisis could still be developing beneath the surface. Cracks could be propagating through the nucleus right now, invisible to our telescopes but inexorably weakening the object. A fragmentation event could occur without warning, transforming a single enigmatic visitor into a swarm of debris. What would fragmentation mean for our understanding of 3I-ATLAS? In some ways, it would simplify the picture. A cometary nucleus that breaks apart under thermal stress is behaving exactly as our models predict. The anomalies, the anti-tail, the non-gravitational acceleration, the unusual spectroscopy, all of these could potentially be explained as consequences of an unstable, fragmenting body. Fragments of different sizes would experience different radiation pressure, potentially creating the complex jet structures we observe. Non-gravitational acceleration could result from asymmetric mass loss as pieces break away. But fragmentation would also represent a loss. 3I-ATLAS is only the third interstellar object we have ever detected. Oumuamua passed through too quickly for extensive study, its small size and lack of cometary activity making it difficult to characterize. Borisov was more cooperative, displaying classic cometary behavior, but it too has now departed our solar system forever. 3I-ATLAS represents our best opportunity yet to study material from another star system, to analyze the chemistry and composition of a body that formed around an alien sun. If it fragments, we will still learn something. The debris field itself would be scientifically valuable, potentially exposing interior material that would otherwise remain hidden beneath the surface. But we would lose the opportunity to study the object as a coherent whole, to understand its structure and history as an integrated system. The parallel with K1-ATLAS raises another question, one with philosophical as much as scientific implications. Why are both objects displaying golden coloration as they enter Leo? Is this pure coincidence, two unrelated comets happening to undergo similar chemical changes while transiting the same region of sky? Or is there some connection we have not yet identified? The rational interpretation is coincidence. Leo is a large constellation, and comets pass through it regularly. The colour shift to gold results from carbon depletion, which occurs in many comets as they approach the Sun. The fact that both Atlas comets are displaying this behaviour simultaneously is striking but not statistically extraordinary when considered against the total population of comets observed over astronomical history. And yet, the human mind seeks patterns, and sometimes patterns are real. Both objects were discovered by the same telescope network. Both are making close approaches to the inner solar system at nearly the same time. Both have shifted through the same colour sequence. Both are transiting through Leo. One has already been destroyed. Whether these parallels represent meaningful connections or pure chance, they have certainly captured public attention. Social media discussions of 3I-ATLAS frequently reference K1's fate as either a warning or a precedent. The astronomical community is watching closely, documenting every observation, preparing for whatever comes next. And something is coming. The December 19th approach will bring answers one way or another. Either 3I-ATLAS will demonstrate its resilience, maintaining structural integrity as it begins its long journey toward Jupiter, an eventual escape from our solar system. Or it will follow K1 into fragmentation, scattering its ancient material across the void. But before we reach that crucial date, we need to address another mystery that has been building since the earliest observations of 3I-ATLAS, a mystery involving one of the most unexpected elements to appear in a cometary spectrum, an element that should be accompanied by its chemical twin but somehow is not, an element whose presence has baffled spectroscopists and fueled speculation about the true nature of this interstellar visitor. The nickel enigma. In the periodic table of elements, nickel and iron sit side by side. They are cosmic twins, forged in the same stellar furnaces, scattered by the same supernova explosions, incorporated into the same planetary bodies throughout the universe. When you find nickel, you expect to find iron. When you find iron, you expect to find nickel. The ratio between them is one of the most consistent chemical signatures in the cosmos, varying only slightly based on the specific conditions of stellar nuclear synthesis that produced them. So when spectroscopic observations of 3I-ATLAS revealed strong nickel emissions but no corresponding iron signature, astronomers around the world did a collective double take. It was as if someone had presented them with a sandwich that contained peanut butter but somehow lacked bread. The combination was so unexpected, so contrary to basic chemistry, that the initial reaction was to assume the data must be wrong. But the data was not wrong. Multiple observations confirmed it. The Very Large Telescope in Chile first detected nickel emission on July 20th of this year, approximately 3 weeks after the initial discovery. Follow-up observations on August 14th detected cyanide as well. Throughout July and August, as 3I-ATLAS approached the Sun, the concentration of nickel in the coma increased steadily. By the time VLT observations concluded on August 21st, 3I-ATLAS was emitting approximately 4.6 grams of nickel per second. 4.6 grams per second. That might not sound like much, but consider the timescales involved. Over a single day, that rate produces nearly 400 kilograms of nickel vapor. Over a month, almost 12 metric tons. This material is being actively released from the nucleus, vaporizing into the coma, spreading into space. And through all of this, the iron emission line remains stubbornly absent. To understand why this is so puzzling, we need to consider how nickel and iron normally behave in comets. Both elements are present in cometary nuclei, bound within minerals and possibly within metallic grains. Under normal circumstances, neither element vaporizes easily. Their boiling points are extremely high, thousands of degrees Celsius, far beyond the temperatures that solar heating can produce at cometary distances. So how does any nickel or iron end up in the gaseous coma? The answer, for most comets, involves a class of compounds called metal carbonyls. These are molecules where metal atoms are bonded to carbon monoxide groups, creating volatile compounds that can sublimate at much lower temperatures than the pure metals. Nickel carbonyl, with the chemical formula NiCO4, volatilizes at temperatures well below 100 degrees Celsius. Iron carbonyl, FeCO5, is similarly volatile. When solar heating warms a cometary nucleus, these carbonyls can sublimate directly into the coma, carrying their metal atoms with them. Once in the coma, the carbonyls are quickly destroyed by solar ultraviolet radiation. The carbon monoxide groups are stripped away, leaving behind free metal atoms that can be detected spectroscopically. This process has been observed in numerous solar system comets, and it typically produces nickel and iron in roughly equal proportions, reflecting their similar abundances in cometary material. 3I-ATLAS breaks this pattern completely. The nickel is there, the iron is not, and the discrepancy is not subtle. We are not talking about a slight imbalance in the nickel-to-iron ratio. We are talking about clear detection of one element and complete absence of the other. Several hypotheses have been proposed to explain this anomaly, each with its own implications for the nature and history of 3I-ATLAS. The first hypothesis involves differential stability of the carbonyl compounds. While both nickel carbonyl and iron carbonyl are volatile, they are not equally stable. Iron carbonyl is more reactive than nickel carbonyl. It can decompose more readily, break down in the presence of other molecules, react with water or other compounds present in the nucleus. If 3I-ATLAS contains significant amounts of water ice in contact with the metal carbonyls, the iron carbonyl might be destroyed before it ever reaches the coma, while the more stable nickel carbonyl survives to release its metal atoms into space. This hypothesis is consistent with the observation that 3I-ATLAS showed strong water activity after crossing the 2.5 astronomical unit threshold in early September. If water sublimation was exposing fresh material that had previously been protected from solar heating, any iron carbonyl in that material might have reacted with the water rather than sublimating intact. The second hypothesis involves the original formation environment of 3I-ATLAS. The relative abundances of nickel and iron carbonyls depend on the conditions under which they formed, particularly the temperature, pressure, and availability of carbon monoxide. If 3I-ATLAS formed in a region where conditions favoured nickel carbonyl formation over iron carbonyl, the resulting body would be enriched in nickel relative to iron from the very beginning. This could tell us something profound about the star system where 3I-ATLAS originated. Our own solar system formed under specific conditions that produced a particular nickel to iron ratio in its comets. A different ratio would indicate different formation conditions, potentially a different type of star, a different protoplanetary disk temperature, a different cosmic environment entirely. The third hypothesis is more exotic and has attracted particular attention from those who suspect 3I-ATLAS may not be entirely natural. What if the selective nickel enrichment is not a result of natural chemistry, but of deliberate processing? Nickel has industrial applications. It is used in alloys, in catalysts, in electronic components. An advanced civilization mining cometary material might preferentially extract iron for structural purposes while leaving nickel compounds behind. The nickel emission from 3I-ATLAS could, under this speculative scenario, be residue from industrial activity. This hypothesis is, to be clear, highly speculative. There is no direct evidence for artificial processing of 3I-ATLAS. The nickel anomaly can be explained through natural chemistry without invoking technological intervention. But the hypothesis illustrates how the unusual properties of this object have captured imaginations and generated theories across the spectrum from conventional to extraordinary. Whatever the explanation, the nickel enigma adds to the list of ways that 3I-ATLAS differs from typical solar system comets. And it is not just the nickel-to-iron ratio that is unusual. The overall abundance of nickel in the coma increased far more rapidly than expected as 3I-ATLAS approached the Sun. Standard models of cometary activity predict gradual increases in gas production as solar heating intensifies. 3I-ATLAS showed a much steeper curve, with nickel emission ramping up sharply in ways that suggested either unusual sensitivity to temperature or unusual internal structure. The cyanide detections add another layer to this chemical puzzle. Cyanide, HCN, is a common molecule in comets, produced when solar radiation breaks apart more complex compounds containing carbon, hydrogen, and nitrogen. Its presence in 3I-ATLAS is not surprising in itself. What is noteworthy is the relationship between cyanide production and nickel production. Both increased in parallel as the comet approached the Sun, suggesting they may be linked to the same source material or the same sublimation processes. One intriguing possibility is that the nickel and cyanide are both being released from the same organic matrix. Complex organic compounds, the kind that give comets their reddish coloration, can incorporate metal atoms within their molecular structures. As these organics sublimate or decompose, they could release both metal atoms and simpler molecules like cyanide simultaneously. This would explain the correlated production rates and potentially the unusual nickel to iron ratio if the organic matrix preferentially incorporates nickel over iron. The organic hypothesis connects back to the colour evolution we discussed earlier. 3I-ATLAS began its passage through our solar system, displaying a deep red colour, attributed to organic compounds accumulated during its journey through interstellar space. As it approached the Sun, these organics began sublimating and decomposing, releasing nickel, cyanide, and eventually the diatomic carbon that produced the green glow. Now, with the organics largely depleted, the object has shifted to golden coloration while the gas production declines. This narrative is internally consistent and fits within known cometary chemistry. But it raises questions of its own. Where did the organics come from? How did they accumulate on the surface of 3I-ATLAS during its interstellar voyage? And why is the nickel to iron ratio so different from what we see in solar system objects? The answer may lie in the interstellar medium itself. Between the stars, space is not completely empty. It contains a thin soup of atoms, molecules, and tiny dust grains, the debris of countless stellar deaths and births. A body travelling through this medium at 61 kilometers per second, as 3I-ATLAS has been doing for billions of years, would continuously sweep up this material. The atoms and molecules would stick to the cold surface, building up a coating of interstellar frost over cosmic timescales. The composition of this frost would depend on what the interstellar medium contains, which varies depending on location in the galaxy. Near regions of recent star formation, the medium might be enriched in certain elements produced by massive stars. Near the remnants of supernovae, the composition would reflect the specific nuclear reactions that occurred in those explosions. The unusual nickel signature in 3I-ATLAS could be a direct measurement of the interstellar medium it has been travelling through, a chemical fingerprint of its journey across the galaxy. This interpretation transforms 3I-ATLAS from merely an unusual comet into a cosmic messenger, carrying information about the chemistry of interstellar space that we could not obtain any other way. Every gram of nickel in its coma, every molecule of cyanide, every grain of reddish organic dust represents material collected over billions of years of wandering between the stars. By studying this material, we are studying the galaxy itself. The James Webb Space Telescope observations scheduled for this month will be crucial for understanding the nickel enigma and the broader chemical story of 3I-ATLAS. Webb's infrared spectrometers can detect molecular signatures that are invisible to optical telescopes, potentially revealing compounds that are present in the coma but have not yet been identified. If there are iron-bearing compounds present but in forms that do not produce visible emission lines, Webb might find them. Webb can also examine the thermal properties of the dust in the coma, determining whether the grains are primarily silicate, carbonaceous, or some mixture. This information would help constrain the formation environment and processing history of 3I-ATLAS, potentially explaining why its chemistry differs so dramatically from solar system comets. The nickel enigma also has implications for the fragmentation question we explored in the previous chapter. Metal carbonyls are volatile compounds that contribute to the overall ice budget of a cometary nucleus. If 3I-ATLAS has unusual abundances of these compounds depleting them more rapidly than expected, the structural integrity of the nucleus could be affected. The nickel emission we observe might be a sign that binding materials within the nucleus are being lost, weakening the object from within. Alternatively, the unusual chemistry might actually enhance structural stability. If 3I-ATLAS has different ice compositions than solar system comets, with different melting points and different thermal expansion coefficients, it might respond to solar heating in ways that our models do not predict. The same chemical differences that produce the nickel anomaly might also produce unexpected resilience. We simply do not know enough yet. 3I-ATLAS is teaching us that interstellar objects can differ fundamentally from the comets we have studied for centuries. Every assumption we make based on solar system experience must be tested against the actual behavior of this alien visitor. And the nickel enigma is one of the clearest reminders that our assumptions may be wrong. But the nickel is only one entry on a growing list of anomalies associated with 3I-ATLAS. As observations have accumulated over the past 5 months, researchers have documented feature after feature that distinguishes this object from any comet in our experience. The full list now extends to 13 separate anomalies, each one a puzzle that demands explanation. Some of these anomalies may prove to be artifacts of observation or consequences of our incomplete understanding. Others may point to genuinely new phenomena that will reshape our conception of interstellar visitors. And at least one researcher has argued that the accumulation of anomalies crosses a threshold, that the probability of all these features occurring together in a natural object is so low that we must consider alternatives. That argument has proven controversial to say the least. But the anomalies themselves are real, documented in peer-reviewed observations and confirmed by multiple independent teams. 13 anomalies and counting science advances by paying attention to the things that do not fit. The observations that defy our models, the data points that fall outside our predictions, the phenomena that refuse to behave according to established theory. Anomalies are not failures of observation, they are invitations to learn, and 3I-ATLAS has issued more invitations than any object in recent astronomical memory. The list of documented anomalies now numbers 13, compiled through months of intensive observation by professional and amateur astronomers worldwide. Each entry represents a feature of 3I-ATLAS that distinguishes it from typical comets, that requires explanation, that pushes against the boundaries of our understanding. Taken individually, any one of these anomalies might be dismissed as statistical fluctuation or measurement error. Taken together, they paint a picture of an object that is genuinely unprecedented. Let us walk through them systematically, understanding what each anomaly represents and why it matters. Anomaly 1. The trajectory of 3I-ATLAS is aligned to within 5 degrees of the ecliptic plane, the flat disk in which the planets of our solar system orbit. For a randomly arriving interstellar object, this alignment has a probability of approximately 0.2%. Most objects entering our solar system from interstellar space would arrive at random angles, crossing the ecliptic at steep inclinations. 3I-ATLAS instead travels almost exactly in the same plane as Earth, Mars, Jupiter, and the other planets. This alignment maximised the number of close planetary encounters during its passage, and, some have noted, minimised the rocket fuel that would be required for a spacecraft to match velocities with our planets. Anomaly 2. The persistent sunward jet, or anti-tail that we discussed in detail earlier. This feature has been present since the first Hubble observations in July, and has grown to extend more than 500,000 kilometres toward the Sun. It defies the basic physics of radiation pressure and has not been satisfactorily explained by any conventional model. Anomaly 3. The nucleus of 3I-ATLAS appears to be approximately 1 million times more massive than Oumuamua and 1,000 times more massive than Borisov, while travelling faster than both previous interstellar visitors. The combination of high mass and high velocity is statistically unlikely, with a probability estimated at less than 0.1% when compared to predicted interstellar object populations. Anomaly 4. The arrival timing of 3I-ATLAS was fine-tuned in a way that brought it within tens of millions of kilometres of Mars, Venus and Jupiter, while making it unobservable from Earth at perihelion. The probability of this particular combination of planetary encounters and Earth geometry has been calculated at approximately 0.005%. The object appeared to thread a needle through our solar system, maximizing scientific opportunities at other planets, while hiding from Earth-based observation during its closest approach to the Sun. Anomaly 5. The direction from which 3I-ATLAS arrived is coincident to within 9 degrees with the famous WOW signal, detected in 1977 by the Big Ear Radio Telescope in Ohio. The WOW signal remains unexplained, a 72-second burst of apparent artificial radio emission that has never been observed again. The angular coincidence between the WOW signal direction and the arrival vector of 3I-ATLAS has a probability of approximately 0.6% if both are random. Anomaly 6. The colour evolution from red to green to gold follows a pattern that, as mentioned, preceded the fragmentation of K1-ATLAS. While colour changes are known to occur in comets, the specific sequence and timing observed in 3I-ATLAS is unusual. Anomaly 7. The nickel emission without corresponding iron that we explored in the previous chapter. This chemical signature has not been observed in any solar system comet and defies the expected chemistry of metal-carbonyl sublimation. Anomaly 8. The non-gravitational acceleration detected by JPL Horizon's tracking, which scales inversely with the square of heliocentric distance. This acceleration pattern is consistent with either massive outgassing or, as some have suggested, technological propulsion. Anomaly 9. The jets emerging from 3I-ATLAS maintain their orientation across scales of millions of kilometres despite the measured rotation period of approximately 16 hours. Over the timescales involved, rotation should smear any jet features into spiral patterns. Instead, the jets remain tightly collimated. Anomaly 10. The brightness increase near perihelion far exceeded standard cometary models. 3I-ATLAS brightened by several orders of magnitude more rapidly than typical Oort cloud comets at similar heliocentric distances, suggesting unusual outgassing behaviour or unusual surface properties. Anomaly 11. The surface area required to absorb enough sunlight to power the observed mass loss exceeds the physical size of the nucleus, as constrained by Hubble observations. At perihelion, calculations suggest that the absorbing area would need to be equivalent to a sphere 23 kilometres in diameter for carbon dioxide ice, or 51 kilometres for water ice. The actual nucleus is estimated at less than 6 kilometres across. Anomaly 12. The antitail maintains coherent structure despite the measured rotation of the nucleus. Whatever mechanism produces this sunward feature must overcome both radiation pressure and rotational effects, which should together destroy any coherent structure over the observed timescales. Anomaly 13. The rapid brightening and subsequent behaviour at perihelion suggests either massive evaporation of at least 13% of the object's total mass, or some other mechanism entirely. If the mass loss was real, the object should have experienced significant structural stress. Yet preliminary post-perihelion images indicate that the nucleus maintained its integrity as a single body. 13 anomalies, each one documented through careful observation, each one representing a departure from expected cometary behaviour. What are we to make of this accumulation? The conservative interpretation is that 3I-ATLAS represents a new class of interstellar comet, formed under conditions different from anything in our solar system, with composition and structure that our models simply do not capture. This is not a dismissal of the anomalies, but an acknowledgement that our sample size of interstellar objects is too small to know what normal looks like. We have observed exactly 3 such objects. Drawing conclusions about typical behaviour from a sample of 3 is statistically meaningless. Under this interpretation, the anomalies are real but not indicative of anything beyond natural variation. Interstellar objects come from diverse environments across the galaxy. Some will have unusual trajectories, some will have unusual chemistry, some will display features we have never seen before. The fact that 3I-ATLAS is unusual does not mean it is unnatural. It means the universe is more varied than we assumed. This interpretation has the virtue of parsimony. It does not require invoking mechanisms or phenomena beyond known physics. It accepts that our models are incomplete and uses 3I-ATLAS as an opportunity to improve them. It is the interpretation favoured by the majority of astronomers studying this object. The alternative interpretation, championed most visibly by Avi Loeb but shared by a minority of researchers and a substantial fraction of the public, holds that the accumulation of anomalies exceeds what can be comfortably attributed to natural variation. Under this view, the coincidences are too numerous, the probabilities too low, the features too coordinated to result from random processes. Something about 3I-ATLAS requires explanation beyond exotic natural chemistry. Loeb has been careful in his most recent writings to maintain epistemic humility. He does not claim that 3I-ATLAS is definitely artificial. He assigns probabilities, currently estimating a 30 to 40% likelihood that the object does not have a fully natural origin. He acknowledges that the most likely outcome remains a natural comet with unusual properties. But he argues that the anomalies warrant serious consideration of alternatives. The specific alternative he has proposed involves technological artifacts. Under this hypothesis, 3I-ATLAS could be a probe sent by an extraterrestrial civilization, deliberately targeting our solar system for reconnaissance or other purposes. The cometary activity would be a disguise, accumulated interstellar material coating an artificial core. The anti-tail could be thrust exhaust. The trajectory alignment could be deliberate navigation. The timing of the passage could be designed to maximize data collection from our planets, while minimizing detection from Earth. This hypothesis makes specific predictions. If 3I-ATLAS is artificial, it should not fragment. Technological artifacts are built to survive, not to crumble under thermal stress. If 3I-ATLAS is artificial, the non-gravitational acceleration should persist even as outgassing declines. Thrusters can operate independently of volatile reserves. If 3I-ATLAS is artificial, close observation might reveal structural features inconsistent with natural objects, perhaps regular geometry, perhaps unusual surface textures, perhaps electromagnetic emissions beyond what cometary activity can explain. The December 19th closest approach will test some of these predictions. High-resolution imaging will constrain the shape of the nucleus. Spectroscopic observations will characterize the outgassing in unprecedented detail. Radio telescopes will listen for any unusual emissions. If 3I-ATLAS behaves exactly like a natural comet, the technological hypothesis will lose support. If it continues to defy expectations, the hypothesis will gain credibility. But we must be careful about how we interpret the evidence. The human mind is prone to seeing patterns where none exist, to assigning meaning to coincidence, to preferring exciting explanations over mundane ones. The history of science is littered with examples of phenomena that seemed anomalous until better observations revealed natural explanations. Canals on Mars, pulsating radio sources that were briefly suspected to be alien beacons before being identified as rotating neutron stars, the anomalous acceleration of Pioneer spacecraft that turned out to result from thermal radiation pressure. Each of these cases involved genuine anomalies that eventually yielded to conventional physics. Each of these cases also involved premature speculation about exotic explanations that proved unfounded. The lesson is not that anomalies should be ignored, but that they should be investigated carefully and patiently, with conclusions proportional to the evidence. 3I-ATLAS has been under intensive observation for less than 6 months. We have data from multiple telescopes across multiple wavelengths, but we're still in the early stages of understanding this object. The anomalies are real, but their interpretation remains uncertain. The responsible scientific approach is to continue gathering data, to test hypotheses against observations, to let the evidence guide conclusions, rather than letting conclusions shape the interpretation of evidence. What we can say with confidence is that 3I-ATLAS is extraordinary regardless of its origin. If it is a natural comet, It is teaching us that interstellar objects can differ profoundly from anything in our solar system. If it is something else, it is teaching us that the universe contains possibilities we had not seriously considered. Either way, we are learning. The 13 anomalies will continue to accumulate or resolve as observations proceed. New features may be discovered, existing features may be explained. The December 19th closest approach will be pivotal, providing data quality that has not been possible at greater distances, and the observations are not limited to Earth-based telescopes. A fleet of spacecraft across the solar system has been tracking 3I-ATLAS, gathering data from perspectives unavailable to ground observers. X-ray satellites have detected emissions from the coma. Infrared instruments have measured thermal signatures. Spacecraft at Mars captured images during the October close approach. This multi-wavelength, multi-platform campaign represents an unprecedented effort to characterize an interstellar visitor. The results of that campaign are still being processed and analyzed. Some findings have already been published, others remain preliminary, awaiting peer review and verification. But taken together, they are building the most complete picture ever assembled of an object from beyond our solar system. In the next chapter, we will examine the X-ray observations in detail. Because when space agencies trained their most sensitive high-energy instruments on 3I-ATLAS, they found something remarkable. An X-ray glow extending hundreds of thousands of kilometers from the nucleus, revealing processes that optical telescopes cannot see. Eyes in space. The X-ray hunt. There is a certain poetry in using X-rays to study a visitor from another star system. X-rays were discovered by Wilhelm Röntgen in 1895 while he was experimenting with cathode ray tubes in his laboratory. He named them X-rays because he did not know what they were. The X represented the unknown, the mysterious, the not yet understood. 130 years later, we point X-ray telescopes at an object whose nature remains equally uncertain, hoping that these high-energy photons will reveal what visible light cannot. The first X-ray detection of 3I-ATLAS came from the Japanese space agency's EXISA mission, the X-ray imaging and spectroscopy mission launched in September 2023. EXISA observed the interstellar visitor during a Target of Opportunity campaign from November 26th through November 28th of this year, accumulating 17 hours of effective exposure time. The observations were challenging because XRISM can only observe targets more than 60 degrees from the Sun, which limited the available window as 3I-ATLAS moved through the inner solar system. The resulting images showed something remarkable: a faint X-ray glow extending approximately 5 arc minutes from the position of 3I-ATLAS, corresponding to a physical scale of roughly 400,000 kilometers at the comet's distance. This glow was not concentrated at the nucleus, but spread diffusely through the surrounding space, tracing the outer regions of the coma. Shortly after the XRISM observations, the European Space Agency's XMM Newton joined the hunt. On December 3rd, XMM Newton trained its European photon imaging camera on 3I-ATLAS for approximately 20 hours when the comet was about 284 million kilometers from Earth. XMM Newton's EPIC PN camera is one of the most sensitive X-ray detectors ever built, capable of registering individual X-ray photons and measuring their energies with precision. Both telescopes detected the same phenomenon. 3I-ATLAS is emitting X-rays, or more precisely, the gas surrounding 3I-ATLAS is producing X-rays through its interaction with the solar wind. To understand why this matters, we need to step back and consider how comets produce X-rays in the first place. It was a surprise when the first cometary X-ray emission was detected by the Rosat satellite in 1996 during observations of comet Hyakutake. Comets are cold objects, far too cold to emit thermal X-rays on their own. The Sun heats their surfaces to modest temperatures, a few hundred degrees Celsius at most, orders of magnitude below the millions of degrees required for thermal X-ray production. So where do the X-rays come from? The answer involves a process called charge exchange. The solar wind, that continuous stream of charged particles flowing outward from the Sun, is composed primarily of protons and electrons, but also contains heavier ions like carbon, nitrogen, and oxygen in various states of ionization. These ions have been stripped of some of their electrons by the extreme temperatures of the solar corona, leaving them hungry to recapture electrons from any available source. When the solar wind encounters the gas cloud surrounding a comet, the ions find what they are looking for. The neutral atoms and molecules in the coma provide electrons that the solar wind ions can capture. This electron transfer is energetically favourable, but the captured electrons often end up in excited states. As they drop down to lower energy levels, they emit photons. And for highly charged ions capturing electrons from neutral targets, those photons are often in the X-ray range. The result is a diffuse glow of X-rays surrounding any active comet, tracing the boundary where solar wind meets cometary gas. The intensity and spectrum of this emission depend on the composition of both the solar wind and the cometary coma, making X-ray observations a powerful tool for studying cometary chemistry. So the detection of X-rays from 3I-ATLAS is not surprising in itself. Any object releasing gas into the solar environment will produce charge exchange X-rays when that gas interacts with the solar wind. What makes the X-ray observations valuable is what they can tell us about gases that are otherwise difficult to detect. Optical and ultraviolet spectroscopy excel at identifying certain molecules, particularly those with strong electronic transitions at convenient wavelengths. But some of the most fundamental molecules in the universe are nearly invisible to these techniques. Molecular hydrogen, H2, the most abundant molecule in the cosmos, has no permanent dipole moment and produces no easily detectable spectral features at optical wavelengths. Molecular nitrogen, N2, faces similar challenges. These molecules can be present in large quantities without showing up in conventional spectroscopic surveys. X-ray observations change this calculus. When solar wind ions undergo charge exchange with hydrogen or nitrogen molecules, they produce distinctive X-ray signatures that can be identified in the resulting spectrum. The Gurism and XMM Newton observations of 3I-ATLAS are specifically designed to search for these signatures to determine whether the coma contains significant reservoirs of hydrogen and nitrogen that have escaped detection through other means. The significance of this cannot be overstated. One of the leading hypotheses for the anomalous acceleration of Oumuamua was that it was composed of exotic ices, possibly pure hydrogen ice or pure nitrogen ice, that would sublime without producing visible gas signatures. Such ices would be invisible to optical telescopes, but could potentially be detected through X-ray charge exchange. If 3I-ATLAS shows evidence of hydrogen or nitrogen enrichment in its X-ray spectrum, it would strengthen the hypothesis that interstellar objects can carry ice compositions fundamentally different from solar system comets. Conversely, if the X-ray spectrum shows only the signatures expected from water and carbon dioxide outgassing, it would support the interpretation that 3I-ATLAS is chemically similar to known comets, despite its exotic origin. The preliminary analysis of the Gurism data, released on December the 6th, shows X-ray excesses at energies corresponding to carbon, nitrogen, and oxygen ions. These are the signatures expected from charge exchange with a typical cometary coma. The glow is diffuse and extends in patterns consistent with the known structure of the gas cloud surrounding 3I-ATLAS. Nothing in the initial data screams artificial or anomalous, but the full analysis is ongoing, and there are subtleties that require careful examination. The relative intensities of different X-ray lines can reveal the composition of the target gas in ways that depend on complex atomic physics. Small variations from expected patterns could indicate unusual molecular abundances. The spatial distribution of the emission could reveal asymmetries or structures not visible at other wavelengths. There is also the question of variability. The solar wind is not constant. It fluctuates in intensity and composition depending on solar activity, coronal holes, and other factors. The X-ray emission from a comet varies accordingly. brightening when solar wind flux increases and fading when it decreases. By monitoring these variations, astronomers can study the dynamic interaction between 3I-ATLAS and its space environment. During the CRISM observation window, the Sun was displaying elevated activity. A large sunspot region was aligned with the direction toward 3I-ATLAS, producing enhanced solar wind flux in the comet's vicinity. This increased activity should have enhanced the X-ray emission, potentially making fainter features detectable that would be invisible under quieter conditions. Some observers have noted with interest that this solar alignment occurred coincidentally with 3I-ATLAS's position in the sky, as if the Sun itself were illuminating the interstellar visitor for our benefit. Such coincidences invite speculation, but require caution in interpretation. The Sun frequently displays active regions, and any comet moving through the inner solar system will periodically find itself aligned with such regions. The alignment observed in December was notable but not unprecedented. What does the X-ray emission tell us about the physical state of 3I-ATLAS? The extended nature of the glow, reaching hundreds of thousands of kilometers from the nucleus, indicates substantial gas production. Material must be flowing outward continuously to maintain a coma of this size against the dissipating effects of solar radiation and solar wind. This is consistent with an actively outgassing comet, but does not necessarily match the surprisingly limited visible gas signatures that some observers have reported. The discrepancy, if real, could indicate that 3I-ATLAS is releasing gas that does not produce strong optical emissions. Molecules like H2 and N2 would fall into this category, along with noble gases like argon or neon. Alternatively, the discrepancy could reflect difficulties in measuring visible outgassing rates, which depend on assumptions about excitation conditions and gas temperatures that may not apply to an interstellar object. The XMM Newton observations from December 3rd add temporal information to the spatial picture from EXORISM. By comparing observations taken a week apart, astronomers can track how the X-ray emission evolves as 3I-ATLAS moves through the solar system and as solar wind conditions change. Any sudden variations could indicate discrete events at the nucleus, perhaps outbursts or structural changes. Steady evolution would suggest a quiescent state consistent with normal cometary activity. The X-ray campaigns also provide opportunities to search for features that would indicate non-natural origins. Technological artifacts might produce X-ray signatures distinct from charge exchange, perhaps from electronic systems, perhaps from nuclear power sources, perhaps from processes we cannot anticipate. The observations have been designed to look broadly, not just for expected signatures, but for any emission that deviates from standard models. So far, nothing unexpected has been reported, but the analysis is ongoing, and the scientific teams involved have been appropriately cautious about preliminary conclusions. X-ray astronomy is a specialized field requiring sophisticated data reduction and careful attention to instrumental effects. Claims about anomalous emission would require extraordinary evidence and would surely invite intense scrutiny from the broader community. What we can say is that 3I-ATLAS is cooperating with the campaign to observe it. Unlike Oumuamua, which was small, dark and inactive, 3I-ATLAS is large enough and active enough to produce detectable signals across multiple wavelengths. Unlike Borisov, which arrived with less advance notice and was observed during a less favourable geometric configuration, 3I-ATLAS has been tracked continuously and will remain observable for months to come. This opportunity has not been wasted. Ground-based telescopes from multiple continents have contributed observations. Space-based assets from NASA, ESA and JAXA have all participated. Amateur astronomers have provided supplementary data that complements the professional campaigns. The result is a dataset of unprecedented richness for an interstellar object. The X-ray observations represent just one slice of this comprehensive effort. Optical telescopes have tracked the colour evolution and structural changes. Infrared instruments have measured thermal properties and searched for molecular signatures. Radio telescopes have listened for unusual emissions and characterized the OH radical production from water photodissociation. Radar facilities have attempted to bounce signals off the nucleus to constrain its size and surface properties. Each technique reveals different aspects of 3I-ATLAS. Each adds pieces to the puzzle, and as the pieces accumulate, a picture is emerging of an object that is genuinely complex, with multiple active processes occurring simultaneously. The X-ray glow traces the outermost reaches of the coma, where cometary gas meets solar wind. The optical emission reveals the dust and small molecules closer to the nucleus. The infrared signatures indicate the thermal state and volatile content. Together, these observations span scales from the nucleus itself, perhaps a few kilometers across, to the outer coma extending millions of kilometers into space. The December 19th closest approach will provide the highest resolution data yet. X-ray observations will reach deeper into the faint emission regions. Optical telescopes will resolve finer details in the coma structure. Spectroscopic campaigns will achieve better signal-to-noise ratios, potentially detecting trace species that have been invisible at greater distances. And then 3I-ATLAS will begin its long journey outward, first toward its March encounter with Jupiter, then into the darkness beyond. The X-ray emission will fade as the object moves farther from the Sun and generates less gas. The optical signatures will dim as reflected sunlight weakens. Eventually, even the largest telescopes will lose track of this interstellar messenger, and it will vanish into the cosmic background from which it emerged. But before that happens, there is another question we must confront. The X-ray observations have shown that 3I-ATLAS is releasing gas at substantial rates. The anti-tail suggests that material is being ejected in unusual patterns. The non-gravitational acceleration indicates that forces beyond gravity are acting on the object. All of this activity puts stress on the nucleus. The question is whether that stress is sustainable, whether 3I-ATLAS can withstand the accumulated effects of its solar passage, whether the gold colour and the chemical depletion are harbingers of destruction, or merely stages in an ongoing evolution. The fragmentation clock is ticking, and as we approach the December 19th window, the entire astronomical community is watching to see whether 3I-ATLAS will remain whole or follow its namesake K1 into dissolution. The fragmentation clock. Every comet that approaches the Sun faces an existential test. The warmth that awakens its dormant ices also threatens to destroy it. Volatiles sublime from the surface, carrying dust and creating the spectacular tales that have inspired awe throughout human history. But that sublimation comes at a cost. Material is lost, mass decreases, internal stresses build as some regions heat faster than others, and for some comets, the test proves fatal. 3I-ATLAS has already survived one critical passage. Its October 29th perihelion brought it within 1.4 astronomical units of the Sun, close enough to experience heating of more than 700 watts per square metre. The object emerged from this encounter apparently intact, resuming its journey through the inner solar system without obvious signs of fragmentation. But the test is not over. Thermal waves propagate slowly through porous, icy material. The surface of a comet responds quickly to changes in solar illumination, heating during the day and cooling at night. But the interior takes much longer to equilibrate. Heat conducts inward over timescales of weeks to months, gradually raising temperatures at depths where the most volatile ices reside. For a nucleus several kilometers in diameter, as 3I-ATLAS may be, the thermal response to perihelion can take many weeks to fully develop. The maximum internal stress may not occur at perihelion itself, but sometime afterward, as accumulated heat reaches structurally critical regions. This delay explains why some comets fragment well after their closest approach to the Sun, surprising observers who assumed the danger had passed. K1-ATLAS illustrated this pattern vividly. It survived its October 8th perihelion, passing within 50 million kilometers of the Sun without immediate incident. For several weeks it appeared to have escaped destruction, but the thermal damage had been done. By early November, outbursts signalled internal disturbances. By November 11th, fragmentation was confirmed. The comet that had defied predictions of its demise finally succumbed to forces that had been building since its solar encounter. The timeline for 3I-ATLAS is different because its perihelion was less extreme. At 1.4 astronomical units, compared to K1's 0.33 astronomical units, the heating was correspondingly milder. Thermal penetration would proceed more slowly, and structural stress would accumulate more gradually. If fragmentation is going to occur, it may not happen for weeks or even months after the patterns that destroyed K1. But the gold colour shift suggests that chemical processes similar to those in K1 are underway. The depletion of carbon-bearing molecules, the transition from gas-dominated to dust-dominated emission, the exhaustion of volatile reservoirs, all of these are warning signs that have preceded fragmentation in previous comets. What would fragmentation look like if it occurs? The process typically begins with small structural failures, cracks propagating through the nucleus along zones of weakness. These cracks can be seeded by thermal stress, by rotational forces, by the pressure of escaping gases seeking pathways to the surface. Once a crack grows large enough, it can penetrate to regions containing concentrated volatiles, triggering sudden releases of gas that widen the crack further. In many cases, the nucleus does not shatter all at once. Instead, fragments carve off one at a time, like icebergs breaking from a glacier. The main body continues on its trajectory, while the fragments drift slowly away, eventually separating enough to be resolved as distinct objects. K1 showed exactly this pattern, splitting into at least 3 major fragments over several days, with each fragment continuing to evolve independently. For 3I-ATLAS, fragmentation would be visible first as asymmetries in the coma. Instead of a smooth, centrally condensed structure, we would see elongation or multiple condensation suggesting more than one source of activity. High-resolution imaging might directly resolve separate fragments if they drift far enough apart. Changes in brightness could indicate exposure of fresh material or the complete disintegration of smaller pieces. Some observers have claimed to see hints of structural change in recent images. Drew Doss, an amateur astronomer who has been closely tracking 3I-ATLAS, posted observations on December 15th, noting what he described as the object appearing to transition from green to gold in multiple independent captures from around the world. He explicitly connected this to K1's colour shift before fragmentation, warning that 3I-ATLAS might be falling apart. Professional astronomers have been more cautious. The official assessment, based on Hubble imagery and ground-based observations through mid-December, is that 3I-ATLAS remains a single coherent body. The coma structure is unusual, with the persistent anti-tail and complex jet features, but there is no clear evidence of nuclear fragmentation. The brightness variations are consistent with changing activity levels rather than structural failure. But the situation is evolving rapidly, and observations from the December 19th closest approach will be decisive. At minimum distance, ground-based telescopes will achieve their highest angular resolution on this object. Any fragments separated by even a few hundred kilometers should be resolvable. Any gross asymmetries in the nuclear region should be visible. The stakes extend beyond scientific curiosity. 3I-ATLAS represents a once-in-a-generation opportunity to study material from another star system. If it fragments, that opportunity will be partially lost. The debris cloud would still be valuable, potentially exposing interior material that would otherwise remain hidden. But we would lose the ability to study the object as an integrated system, to understand its structure and history as a coherent whole. Interstellar objects are rare. Our detection capabilities are improving, but we still expect to find only a handful per decade with current technology. The Vera Rubin Observatory, coming online now, will dramatically increase our discovery rate, but 3I-ATLAS may remain the largest and most active interstellar visitor for years to come. Losing it to fragmentation before we have fully characterized it would be scientifically tragic. There are reasons for optimism, however. The leading hypothesis about 3I-ATLAS's history suggests that it was once a short-period comet around its host star, undergoing hundreds or thousands of close solar approaches before being ejected into interstellar space. This prior thermal processing would have removed the most volatile and structurally weak components, leaving behind a nucleus that has already been tested and tempered. Such an object might be more resilient than a pristine Oort cloud comet like K1, which was making its first approach to any star. The surface of 3I-ATLAS has likely been desiccated to considerable depth, with the most dangerous volatiles long since exhausted. What remains may be a relatively stable core that can withstand the mild heating of its passage through our solar system. The radiation damage detected by James Webb Space Telescope observations supports this interpretation. The surface of 3I-ATLAS shows evidence of cosmic ray exposure extending up to 20 meters deep, indicating billions of years of travel through interstellar space. This damaged layer may act as an insulating crust, protecting the interior from rapid temperature changes and reducing thermal stress. Furthermore, the size of 3I-ATLAS works in its favor. Larger nuclei have more thermal inertia, meaning they heat and cool more slowly. The interior of a 5-kilometer body responds very differently to solar illumination than the interior of a 500-meter body. Temperature gradients are smaller, thermal stresses are reduced, and the risk of catastrophic failure is correspondingly lower. But we cannot be certain until we observe. The gold color shift remains concerning. The elevated activity levels suggested by the anti-tail and jets indicate ongoing processes that could destabilize the nucleus. The non-gravitational acceleration implies forces acting on the object that could include asymmetric mass loss, which could itself trigger structural failure. The December 19th observation window coincides with a new moon, providing the darkest possible skies for ground-based observers. This timing is fortunate and will maximize the scientific return from the closest approach. Amateur astronomers with appropriately sized telescopes, generally 30 centimeters or larger, will have opportunities to image the object under optimal conditions. Professional observatories have prepared intensive campaigns. The Hubble Space Telescope will capture high-resolution imagery that can resolve structures down to a few thousand kilometers. The James Webb Space Telescope will examine the infrared signatures in unprecedented detail. Ground-based spectroscopy will characterize the gas emission with sensitivity unavailable at greater distances. If fragmentation occurs, these observations will document it in real time. If 3I-ATLAS remains intact, they will provide the most detailed portrait yet of an interstellar visitor. Either outcome advances our understanding. Either outcome rewards the extraordinary effort that has gone into this observing campaign. But I suspect that most observers are hoping for intact survival, not because fragmentation would be scientifically uninteresting, but because intact survival would mean continued opportunities to study this object as it journeys toward Jupiter and eventually departs our solar system. Every additional month of observation adds to our understanding. Every additional dataset constrains models and tests hypotheses. The longer 3I-ATLAS remains whole, the more we learn. The fragmentation clock is ticking, driven by thermal processes that we can model but not directly observe. The heat deposited at perihelion continues to propagate inward, raising temperatures in regions that have been cold for billions of years. Volatile ices that survive the journey through interstellar space may now be sublimating for the first time since their parent star system existed. What happens next depends on details of composition and structure that we do not fully know. The porosity of the nucleus, the distribution of volatiles, the strength of the material binding the object together. These parameters vary enormously among solar system comets and are completely unknown for interstellar visitors. We are about to find out. The December 19th closest approach will be the Crucible. If 3I-ATLAS emerges intact, it will have passed a test that destroys many comets far less exotic than itself. If it fragments, it will have joined the long list of objects that underestimated the destructive power of our sun. Either way, the observation will be historic. Either way, we will learn something new about the universe and its wandering messengers. And either way, 3I-ATLAS will have given us something precious. A window into realms we cannot otherwise reach. A visitor from the darkness between stars. The clock is ticking. The telescopes are ready. And in just a few days we will have our answer. But whatever happens on December 19th, it will not be the end of the story. Because 3I-ATLAS is not just passing through our solar system. It is heading toward a specific destination. A world that has captivated human imagination for centuries. In March of 2026, our interstellar visitor will make its closest approach to Jupiter, the king of planets. And that encounter may reveal aspects of 3I-ATLAS that remain hidden from our current vantage point. The December 19th window. In 3 days, something extraordinary will happen. An object born around another star older than our solar system, travelling faster than any human-made spacecraft, will reach its closest point to Earth. 269 million kilometres will separate us from 3I-ATLAS on December the 19th, 2025. That distance is vast by human standards, nearly twice the distance from Earth to the Sun. But by astronomical standards, it is a whisper. It is close enough to resolve details that have been invisible at greater distances. Close enough to measure spectra with unprecedented precision. Close enough to answer questions that have been building since July. And the timing could not be better. December 19th falls on a new moon. The lunar disk, which would otherwise scatter light across the night sky and wash out faint details, will be absent. Observers will work under the darkest conditions available, with nothing to compete against the faint glow of our interstellar visitor. For those who wish to see 3I-ATLAS with their own eyes, the window is now. The object rises in the east before midnight, climbing higher as the hours pass, reaching its most favourable position in the pre-dawn sky. At mid-northern latitudes, it will stand more than 40 degrees above the horizon by 4 in the morning local time. That is high enough to see clearly above most atmospheric turbulence, in the direction where sky darkness is optimal. But I must be honest about what observers will actually see. 3I-ATLAS is currently shining at approximately 11th magnitude, which is far too faint for the naked eye. Even under perfect conditions, the unaided human eye can detect only objects brighter than about 6th magnitude. 3I-ATLAS is approximately 100 times fainter than that threshold. Binoculars will not help much either. Meaningful observation requires a telescope with an aperture of at least 30 centimetres, approximately 12 inches, and preferably larger. Through such a telescope, 3I-ATLAS will appear as a small fuzzy patch, slightly elongated, with perhaps a hint of condensation at the centre. It will not look like the dramatic images captured by Hubble or Webb. It will not display obvious colour to the visual observer, since human colour vision fails at such low light levels. But it will be there, an actual photon entering your eye from an object that has travelled across the galaxy. There is something profound in that directness, that connection between observer and observed. For those with imaging equipment, the opportunities are considerably richer. Modern CMOS cameras can accumulate light over minutes or hours, revealing details invisible to the live view. Colour information emerges from stacked exposures. Structural features become apparent. The anti-tail, the jets, the complex coma morphology, all of these can be captured by dedicated amateurs with appropriate equipment. The professional observing campaign for December 19th is extensive. More than 80 observers have signed up through the United Nations International Asteroid Warning Network, a program specifically designed to track potentially hazardous objects and refine their orbital parameters. 3I-ATLAS poses no threat to Earth, but its inclusion in the IA-1 campaign reflects both its scientific importance and the international cooperation that modern astronomy requires. James Bauer, the principal investigator leading the IAW and 3I-ATLAS campaign, has stated that the program is about halfway through its planned observation period and expects to publish comprehensive findings in a peer-reviewed journal next year. The data being collected includes precise astrometry to refine the object's trajectory, photometry to monitor brightness variations, and spectroscopy to characterize gas emission. Each observation contributes to a growing database that will enable detailed modelling of 3I-ATLAS's properties and behaviour. The Hubble Space Telescope has already delivered multiple high-resolution images and is scheduled for additional observations around the closest approach window. Hubble's angular resolution exceeds anything achievable from the ground, allowing it to resolve structures in the inner coma that would blur together in terrestrial observations. The ultraviolet spectroscopy capability is particularly valuable, probing gas species that are invisible at optical wavelengths. The James Webb Space Telescope brings complementary capabilities. Its infrared instruments can detect thermal emission from the dust in the coma, measure the temperatures of different grain populations, and identify molecular species through their vibrational signatures. Webb observed 3I-ATLAS in August and is scheduled for additional observations in December. The infrared perspective reveals aspects of the object that optical telescopes simply cannot see. Ground-based facilities around the world have devoted significant time to 3I-ATLAS observations. The Very Large Telescope in Chile, the Gemini telescopes in Hawaii and Chile, the Gran Telescopio Canarias in the Canary Islands, and numerous smaller facilities have all contributed data. This distributed effort ensures that weather at any single site does not compromise the campaign. If clouds obscure the sky in Hawaii, observations continue in Chile. If Chile is affected, Europe takes over. The interstellar visitor is never out of sight for long. Radio telescopes have also participated, though their contributions are different in character. Radio observations can detect the OH radical, produced when solar ultraviolet radiation breaks apart water molecules in the coma. The intensity of OH emission provides an independent measure of water production rates, complementing the optical and infrared determinations. Radio facilities can also search for unusual signals that might indicate non-natural origins, though no such signals have been reported. What specific questions will the December 19th observations address? Several are on the priority list. First, the structural integrity of the nucleus. High-resolution imaging will reveal whether 3I-ATLAS remains a single body or has begun to fragment. Any departure from a centrally condensed coma structure would be significant. Multiple condensations, asymmetric morphology, or rapid brightness fluctuations could all indicate nuclear breakup. Second, the nature of the anti-tail. At closest approach, the sunward extension will be imaged at maximum resolution. The detailed structure of this feature, whether smooth or filamentary, coherent or diffuse, will constrain theories about its origin. If the anti-tail is composed of large particles, as some models suggest, it should show different scattering properties than a dust tail composed of smaller grains. Third, the chemical composition of the coma. Spectroscopy at closest approach will achieve the best signal to noise ratios of the entire passage. Trace species that have been undetectable at greater distances may reveal themselves. The relative abundances of different gases, and how those abundances have changed since perihelion, will illuminate the thermal and chemical processes occurring within the nucleus. Fourth, the non-gravitational acceleration. Precise astrometry will refine measurements of how 3I-ATLAS's trajectory deviates from pure gravitational motion. Changes in the acceleration profile since perihelion would indicate evolving outgassing patterns or other processes affecting the object's dynamics. Fifth, any unexpected phenomena. Science proceeds by surprises, and 3I-ATLAS has already delivered more than its share. The observing campaigns are designed to capture whatever presents itself, not just to confirm existing expectations. The geographic distribution of observers favours Northern Hemisphere locations for the December 19th window. 3I-ATLAS will be positioned in the constellation Leo, which rises high in the sky at mid-northern latitudes during the pre-dawn hours. Southern Hemisphere observers can see the object but at lower elevations, which degrades image quality due to atmospheric effects. For viewers in North America, the optimal observation time is roughly 3 to 5 in the morning local time on December 19th, and the nights immediately surrounding that date. The comet will be located just under Regulus, the brightest star in Leo, making it relatively easy to locate with star charts or planetarium software. Stellarium, a free program available for personal computers, can generate custom finder charts for any location and time. For European observers, the timing shifts earlier, with the object well positioned during the late night and early morning hours of local time. For Asian observers, the window falls in the late evening to midnight hours. Everywhere on Earth that can see Leo will have some opportunity to observe, though conditions vary with latitude and local horizon obstructions. What should observers document if they successfully image 3I-ATLAS? Several aspects are scientifically valuable even from modest equipment. The overall brightness, estimated through comparison with nearby stars of known magnitude, contributes to the light curve database. The apparent size and shape of the coma, measured in arc seconds or arc minutes, tracks the extent of the visible activity. Any obvious structural features such as jets or asymmetries should be noted and reported. Professional astronomers welcome contributions from the amateur community, provided observations are made carefully and reported accurately. The American Association of Variable Star Observers maintains a Comets section that accepts reports in standard formats. The International Astronomical Union's Central Bureau for Astronomical Telegrams publishes significant findings. Online communities like Cloudy Nights and Ice in Space provide forums for sharing images and discussing observations. The December 19th window will be brief in astronomical terms. Within a few days, 3I-ATLAS will begin receding from Earth, the angular size of the coma will shrink, and the opportunities for high-resolution observation will diminish. By January, the object will be significantly fainter and more challenging to observe. By February, only the largest professional telescopes will maintain meaningful contact. The closest approach is truly a critical moment, the best chance we will have to study this interstellar visitor before it departs forever. I encourage anyone with suitable equipment to attempt observation. Even if the results are modest compared to professional imagery, there is value in personal experience. Seeing 3I-ATLAS with your own eyes, through your own telescope, connects you to something vast and ancient. The photons you detect left the surface of that object approximately 15 minutes earlier, reflected from sunlight that itself travelled 8 minutes from our star. But the object itself has travelled for billions of years, crossing unimaginable distances, passing through the territories of countless unknown stars. For one brief window, our paths intersect. For one brief window, we can reach out with our instruments and touch something from another world. After December 19th, 3I-ATLAS will continue its journey, heading toward Jupiter and then beyond, back into the darkness between stars. We will watch it fade. We will analyze the data. We will build models and test theories. But we will never see this particular visitor again. The universe is full of such encounters, connections that flare briefly and then vanish. Ships passing in the night on a cosmic scale. Most of them go unnoticed, objects drifting through our solar system without any observer to mark their passage. 3I-ATLAS is different. 3I-ATLAS was caught, detected, tracked, studied. It will not slip away unnoticed. And if the observations reveal something unexpected, if the data forces us to revise our understanding of what interstellar objects can be, then December 19th, 2025 will be remembered as the date when everything changed. The telescopes are aligned. The observers are ready. The countdown has begun. In 72 hours, more or less, 3I-ATLAS will reach perigee, minimum distance, closest approach. What we find there will write the next chapter in a story that has been unfolding since July. But even as we focus on December 19th, we must remember that the journey of 3I-ATLAS does not end with its closest approach to Earth. there is another encounter ahead, one that may prove equally significant. In March of 2026, 3I-ATLAS will pass within 54 million kilometres of Jupiter, close enough to be influenced by the giant planet's immense gravity. And that passage could reveal secrets that our current vantage point cannot access. The mothership hypothesis. We have spent hours now examining the scientific evidence surrounding 3I-ATLAS. We have discussed its colour transformations, its anomalous anti-tail, its unusual chemistry, its 13 documented departures from expected cometary behaviour. We have approached this object as scientists should approach any new phenomenon, with rigorous attention to data and cautious interpretation of observations. But there is another conversation happening in parallel, a conversation that has captured the attention of millions of people worldwide, that has generated viral social media posts and prime-time news coverage, that has sparked debates in comment sections and podcasts and dinner tables across the globe. This conversation asks a question that science cannot definitively answer, but cannot completely dismiss. What if 3I-ATLAS is not a comet at all? What if it is something else, something constructed, something sent? The most prominent voice raising this possibility is Avi Loeb, the Frank B. Baird Jr., Professor of Science at Harvard University and former chair of the Harvard Astronomy Department. Loeb is not a fringe figure. He has published hundreds of peer-reviewed papers, supervised dozens of doctoral students, and held leadership positions at major scientific institutions. His credentials are impeccable by any standard measure. Yet Loeb has spent the past several years pursuing research that many of his colleagues consider speculative at best and irresponsible at worst. He has suggested that our first interstellar visitor, Oumuamua, might have been an artificial object, a light sail or piece of technological debris from another civilization. He has conducted expeditions to recover materials from the ocean floor that he believes may be fragments of an interstellar meteor. And since July of this year, he has been writing daily blog posts cataloguing the anomalies of 3I-ATLAS and arguing that its unusual properties warrant serious consideration of technological origins. Loeb's hypothesis, in its strongest form, proposes that 3I-ATLAS could be a spacecraft disguised as a comet. Under this scenario, the cometary activity we observe would result not from natural ice sublimation, but from accumulated interstellar material coating an artificial core. The anti-tail could be thrust exhaust rather than injected debris. The trajectory alignment with the ecliptic plane could be deliberate navigation rather than random chance. The timing of the passage, which brought 3I-ATLAS close to multiple planets, while hiding it from Earth observation at perihelion, could reflect a planned reconnaissance mission. He has even suggested in what he describes as a dark forest scenario borrowed from science fiction that 3I-ATLAS could pose a potential threat. If it is a technological artifact with unknown intentions, the possibilities range from benign scientific observation to something more troubling. A probe sent to gather intelligence, a scout for a larger mission. A Trojan horse concealing capabilities we cannot imagine. I want to be extremely careful in how we discuss this hypothesis. It is not the scientific consensus. The overwhelming majority of astronomers studying 3I-ATLAS conclude that it is a natural comet, unusual in its properties, but not artificial in its origin. NASA, ESA, and other space agencies have explicitly stated that 3I-ATLAS is a comet and poses no threat. The evidence for technological origins is circumstantial at best, consisting primarily of an accumulation of anomalies rather than any direct detection of artificial signatures. But Loeb raises valid points about the limitations of our knowledge. We have detected exactly 3 interstellar objects in human history. We have no baseline for what normal interstellar objects should look like. Our models of cometary behaviour are built entirely from solar system objects, which formed in a single environment under a single set of conditions. Extrapolating those models to objects from other star systems is a leap of faith that may or may not be justified. Furthermore, the history of science is full of discoveries that, violated contemporary expectations. Pulsars were briefly suspected to be alien signals before being identified as rotating neutron stars. The cosmic microwave background was mistaken for instrument noise before being recognized as the echo of the Big Bang. Black holes were considered mathematical curiosities before being confirmed as real objects. Science advances by taking seriously the observations that do not fit, even when they seem to point toward unlikely conclusions. The specific anomalies that Loeb has documented are not imaginary. The trajectory alignment is real. The anti-tail is real. The nickel chemistry is real. The non-gravitational acceleration is real. Each of these features requires explanation, and while natural explanations exist for all of them, the combination of multiple unlikely features in a single object is statistically notable. Loeb's approach is to assign probabilities. He does not claim certainty about 3I-ATLAS's nature. Instead, he estimates a 30 to 40% likelihood that the object does not have a fully natural origin, with the remaining 60 to 70% assigned to exotic but natural cometary processes. This is a Bayesian framework, updating prior beliefs based on accumulating evidence. It is a legitimate way to reason about uncertain phenomena. Critics argue that Loeb's priors are too high, that he is too quick to entertain technological explanations when natural ones remain viable. They point out that extraordinary claims require extraordinary evidence, and that anomalies alone do not constitute such evidence. They worry that speculation about alien technology distracts from legitimate scientific investigation and feeds conspiracy theories that undermine public understanding of astronomy. There is merit to these criticisms. The online discourse surrounding 3I-ATLAS has become polluted with misinformation, with false claims about trajectory shifts and hidden NASA images and impending impacts that have no basis in observational data. Approximately 40% of social media posts about 3I-ATLAS invoke aliens or extraterrestrial technology, according to one analysis. This speculation is not Loeb's fault directly, but his public statements have provided fuel for narratives that extend far beyond his scientific claims. At the same time, shutting down inquiry because it might be misused is not a satisfying response. Scientists should not be afraid to ask questions, even uncomfortable ones, even questions that make their colleagues roll their eyes. The history of astronomy is a history of expanding the scope of the possible, of discovering that the universe is stranger and more varied than we assumed. So let us consider the technological hypothesis on its merits. What would we expect to see if 3I-ATLAS were actually an artificial object? First, we would expect it to survive passage through the inner solar system without fragmentation. Technological artifacts are engineered for durability. They do not crumble under thermal stress the way natural comets often do. If 3I-ATLAS remains intact through December 19th and beyond, it passes one test that is consistent with artificial origin, though also consistent with robust natural composition. Second, we would expect the non-gravitational acceleration to persist even as outgassing decreases. Natural cometary acceleration depends on volatile sublimation, which should decline as the comet moves away from the Sun. Technological propulsion could continue regardless of solar distance. Tracking the acceleration profile over the coming months will test this prediction. Third, we might expect unusual electromagnetic emissions. Technological systems require power and may produce detectable signals. Radio telescopes have been listening to 3I-ATLAS since its discovery, and no artificial signals have been detected. This is a negative result that weighs against the technological hypothesis, though it does not definitively refute it. A sufficiently advanced technology might be indistinguishable from natural processes. Fourth, we would expect the accumulated interstellar material to eventually be depleted, revealing whatever lies beneath. If 3I-ATLAS is artificial, its coating of cometary ice should be finite. Continued solar heating should erode this coating until the underlying structure is exposed. We have not seen any indication of this, but the timescale could extend beyond our observation window. The technological hypothesis also makes predictions about what we should not see. An artificial object should not fragment. It should not display chaotic, random outbursts. It should not lose structural coherence in ways that would compromise its mission. Each observation of normal cometary behavior weighs against the hypothesis, while each anomaly provides circumstantial support. The scientific community's rejection of the technological hypothesis is not arbitrary. It reflects the principle of parsimony, the preference for simpler explanations over more complex ones when both fit the data. A natural comet with unusual properties requires fewer assumptions than an artificial spacecraft disguised as a comet. The burden of proof lies with the extraordinary claim. But parsimony is a guideline, not a law. Sometimes the complex explanation is correct. Sometimes the simpler explanation fails to account for critical details. The purpose of observation is to distinguish between hypotheses, to let the universe tell us which interpretation better captures reality. December 19th and the months that follow will provide opportunities to test the technological hypothesis. If 3I-ATLAS behaves exactly as a natural comet should, the hypothesis loses support. If it continues to display anomalies that resist conventional explanation, the hypothesis gains credibility. Either way, we learn something. What Loeb has contributed, for better or worse, is a framework for thinking about observations that might otherwise be ignored. By articulating the technological hypothesis clearly, by specifying what evidence would support or refute it, he's created a testable proposition. That is the essence of scientific methodology, however controversial the proposition itself may be. The Galileo project, which Loeb founded and directs, has deployed observatories to systematically search for anomalous aerial phenomena and unusual objects in Earth's atmosphere. 3 of these observatories, located in Massachusetts, Pennsylvania, and Nevada, are monitoring the sky during the closest approach of 3I-ATLAS. If the object releases any probes or exhibits any behavior that would be detectable from Earth's surface, these instruments are positioned to record it. This is science at the edge, operating in territories where mainstream researchers are reluctant to venture. It invites ridicule and skepticism. It also invites the possibility of discovery. I do not know what 3I-ATLAS is, neither does Loeb, neither does anyone else. The data we have accumulated constrains the possibilities, but does not uniquely identify the truth. We are in a state of genuine uncertainty, which is uncomfortable but honest. What I know is that 3I-ATLAS is extraordinary regardless of its origin. If it is a natural comet, it is teaching us that interstellar objects can be far stranger than we expected. If it is something else, it is teaching us that the universe contains possibilities we had not seriously considered. Either lesson is valuable. Either lesson expands our understanding. And either lesson will become clearer as we observe this object through its closest approach, toward its encounter with Jupiter, and eventually toward its departure from our solar system. The mothership hypothesis may prove to be fantasy, a modern myth projected onto an ancient traveller. Or it may prove to be a glimpse of something real, a recognition that we are not alone in a universe vast beyond comprehension. We will not know until we look. And in the meantime, there is Jupiter, the king of planets, waiting at the outer edge of the inner solar system. In March of 2026, 3I-ATLAS will pass close enough to feel its gravitational pull, close enough to be examined by spacecraft already orbiting the giant planet. What that encounter might reveal is the subject of our final chapter in this journey. What Jupiter will reveal 3I-ATLAS is not finished with our solar system. The December 19th closest approach to Earth is a milestone, not a destination. After passing through the inner solar system, after surviving its perihelion encounter with the Sun, after transforming from red to green to gold under the gaze of 100 telescopes, our interstellar visitor has one more appointment to keep. On March 16th, 2026, 3I-ATLAS will pass within 54 million kilometers of Jupiter. That is roughly 1/3 of the distance from Earth to the Sun, close enough for the giant planet's gravity to measurably affect the comet's trajectory, close enough for Jupiter-based observations to reveal details invisible from our terrestrial vantage point. Jupiter is not merely a planet, it is a gravitational lens that has shaped the architecture of our solar system for 4.5 billion years. Its mass, more than twice that of all other planets combined, dominates the outer solar system. Asteroids and comets feel its pull from hundreds of millions of kilometers away. Entire populations of small bodies have been sculpted by its influence, captured into resonant orbits, flung into the inner solar system, or ejected entirely into interstellar space. For 3I-ATLAS, the Jupiter encounter represents both a scientific opportunity and a potential turning point. The gravitational interaction will refine our understanding of the object's mass and density. The viewing geometry will allow observations from angles unavailable from Earth, and the passage itself will test the structural integrity of a nucleus that has already been stressed by solar heating. The European Space Agency's JUICE spacecraft, the Jupiter Icy Moons Explorer launched in April 2023, is currently en route to the Jupiter system. It will not arrive until 2031, far too late to observe 3I-ATLAS directly. But other assets are available. NASA's Juno spacecraft has been orbiting Jupiter since 2016 and remains operational. While Juno was designed primarily to study Jupiter itself, its instruments have capabilities that could be turned toward an interstellar visitor passing nearby. Whether Juno will be tasked with 3I-ATLAS observations remains to be determined. Mission planning is complex, and diverting resources from primary science objectives requires careful justification. But the opportunity is unprecedented. No spacecraft has ever been in position to observe an interstellar object at close range. Juno's cameras and spectrometers could capture data fundamentally different from anything achievable from Earth. The Jupiter encounter also carries risks. Gravitational perturbation will alter 3I-ATLAS's trajectory in ways that depend sensitively on the object's exact path and Jupiter's exact position. Small uncertainties in either parameter translate to larger uncertainties in the post-encounter trajectory. For scientists tracking 3I-ATLAS into the outer solar system, the Jupiter flyby introduces complications that must be carefully modelled. More speculatively, the gravitational stress of the encounter could affect a nucleus already weakened by solar heating. Jupiter's tidal forces at 54 million kilometers are modest compared to the Sun's influence at perihelion, but they add to cumulative damage. If 3I-ATLAS is on the verge of fragmentation, the Jupiter passage could be the final straw. Or, conversely, if 3I-ATLAS survives the Jupiter encounter intact, it will have passed every test our solar system can offer: solar heating, gravitational perturbation, cosmic ray bombardment during billions of years of interstellar travel. Whatever 3I-ATLAS is made of, it will have proven itself remarkably durable. After Jupiter, 3I-ATLAS will head outward into the darkness. It will cross the orbit of Saturn, then Uranus, then Neptune, fading from view as it recedes from the Sun's light. By the early 2030s, it will have left the planetary region of the solar system entirely, entering the realm of the Kuiper Belt and beyond. Eventually, it will pass through the Oort cloud, that vast spherical shell of dormant comets that marks the outer boundary of the Sun's gravitational influence, and then it will be gone, returning to interstellar space, continuing its journey toward destinations we cannot predict. Where will 3I-ATLAS go? Its trajectory, modified by the gravitational encounters in our solar system, will carry it in a new direction relative to its arrival vector. It will travel for millions of years, perhaps billions, before encountering another star system. It may pass through dozens of stellar neighborhoods without ever being detected, a silent wanderer in the cosmic void. Or it may eventually find a world like ours, a world with observers, a world with telescopes, a world where beings with curious minds look up at the sky and notice something moving against the stars. If 3I-ATLAS is natural, Such observers will find an ancient comet, weathered by countless stellar encounters, carrying the chemical fingerprints of its long journey. If 3I-ATLAS is something else, they will find whatever we ourselves have failed to recognize. The thought is humbling. We are not the first observers to see this object unless we happen to be. Stars have formed and died during 3I-ATLAS's journey. Civilizations may have risen and fallen on worlds we will never know. The interstellar messenger carries a history longer than humanity, longer than Earth, longer perhaps than our Sun. And yet here we are at this moment, with our telescopes and our spectrometers and our insatiable curiosity, trying to understand, trying to read the message written in photons reflected from an icy surface, trying to decode the chemistry of a coma that formed around an alien star, trying to connect, however briefly, with something beyond ourselves. That is what science does. It reaches across distances, it bridges times, it transforms the strange and distant into the known and understood. And when understanding proves elusive, as it sometimes does, science remains present, observing, recording, waiting for the next piece of evidence that might shift the picture. 3I-ATLAS has been a remarkable teacher these past 5 months. It has shown us that interstellar objects can be large, active, and complex. It has revealed chemistry different from our solar system comets. It has displayed features that we are still working to explain. Whether natural or otherwise, it has expanded our conception of what wanders between the stars. The December 19th closest approach will be the climax of this particular chapter of observation. But the story continues. The data we collect will be analysed for months and years. The papers will be written and debated. The models will be revised and refined. And eventually, decades from now, we will look back on this period as the time when we first truly understood interstellar visitors, or as the time when we glimpsed something we were not yet ready to comprehend. I do not know which it will be. I do not think anyone does. The universe keeps its secrets until we earn them through patient observation and rigorous analysis. What I know is that tonight, somewhere on Earth, an astronomer is preparing their telescope, aligning the optics, cooling the camera, consulting star charts to find the exact position of 3I-ATLAS in the constellation Leo. And when the clock strikes the right hour, when the object rises above the horizon, they will open the shutter and begin collecting light. Those photons have travelled for 15 minutes from the surface of 3I-ATLAS to reach that telescope. But the story they carry is billions of years old. It is a story written in nickel and cyanide, in diatomic carbon and water ice, in the dust of organic molecules accumulated during the longest journey any of us can imagine. We are privileged to be the ones who read it. And so, as we come to the end of tonight's exploration, I want to thank you for joining me on this journey through the mysteries of 3I-ATLAS. We have covered a great deal of ground, from the gold metamorphosis to the sunward jet, from the nickel enigma to the mothership hypothesis. We have examined 13 anomalies and found that each one opens more questions than it answers. We have looked through the eyes of X-ray telescopes and contemplated the fragmentation clock that may or may not be ticking toward destruction. Through it all, 3I-ATLAS has remained what it was when we first detected it in July, an enigma wrapped in a coma of gas and dust, travelling through our solar system on a path it has followed for longer than our species has existed. The December 19th observation window begins in 3 days. If you have the equipment and the inclination, I encourage you to look. Find Leo in the pre-dawn sky. Locate Regulus, the brightest star in the constellation, and just below it, a faint fuzzy patch that you might mistake for a distant galaxy or a smudge on your eyepiece. That is 3I-ATLAS. That is a visitor from another star. And for this brief window, it is close enough to touch with light. Whatever you conclude about its nature, whatever hypothesis seems most compelling to you, take a moment to appreciate the sheer improbability of this encounter. An object had to form around another star. It had to be ejected into interstellar space. It had to travel for billions of years on a trajectory that would bring it through our solar system. And it had to arrive during the tiny sliver of cosmic time when a species existed on Earth, capable of detecting and studying it. All of those conditions had to be met. And they were. We're lucky to be here. We're lucky to witness this. And we're lucky to have each other, a global community of observers and thinkers and dreamers, united in our desire to understand the universe and our place within it. Thank you for watching. Thank you for listening. Thank you for caring about a speck of light moving through the darkness of space. If you enjoyed this deep dive into the mysteries of 3I-ATLAS, please consider giving this video a like. It helps more than you know. And if you are not already subscribed, this would be a wonderful time to join our community of curious minds exploring the cosmos together. As always, the information presented here is based on current scientific understanding and is subject to revision as new data emerges. I encourage you to follow the ongoing observations, to read the papers as they are published, to form your own conclusions based on evidence rather than speculation. The sky is vast, the universe is old, and every night, if we choose to look, there are wonders waiting to be seen. Good night, my friends, clear skies, and may your telescopes always find what you're searching for.